Okay, today we will cover the topic of scan chains. Scan chains are a feature of test logic that we implement in order to test chips after they're manufactured. So let's start by talking about testing. After a chip is manufactured, it has to be tested to ensure it is defect-free. Testing is to catch manufacturing defects, not design bugs. So if there is a bug in the design, then and if the silicon is manufactured with that bug, then that bug has become a feature. And testing is going to test the chip only for defects, not for design bugs. So examples of manufacturing defects are shorts. So if a wire is broken, then you would have a short. The other way. An open is a broken wire. So opens are a kind of defect. Shorts would be actual connections between two wires due to a defect. Excessively high resistance of a wire if during fabrication, if something went wrong, and some net may have may not have been may have some defects and manifest very high resistance. Or sometimes, or at the transistor level, there can be defects, like gate oxide defects, which may cause a short between gate and source drain, or some other defect during implantation that may lead to high threshold voltages. So there are any number of possible defects when a chip is being manufactured. And the idea of testing a chip is that whatever defect that there may be that may cause the chip to malfunction, we should be able to catch it before the chip is sold to a customer. So the bottom line is that no chip that a company manufactures should be delivered to customer if it has a defect. And the purpose of testing is to make sure that only defect-free devices reach the end user. So in order to test a chip is not trivial. A chip has many nodes, millions of transistors, hundreds of thousands or even millions of gates. There may be analog circuits, I/O circuits, any number of circuits are there. Any of them may have a defect, and testing has to be very thorough and exhaustive in order to ensure that the chip is truly defect-free. So to do this, we usually have to add some additional circuitry to the chip for testing the chip. And the only purpose of that circuitry is for testing. There's no functional purpose for it. And the chips themselves are designed to operate in two modes. We call them functional and test modes. In normal use, the chip will be in functional mode. So the functional mode, by as the name indicates, is the mode in which the chip is actually serving its purpose and functioning in the system. So that is the functional mode. When the chip is being tested, when it's on the tester, we put the chip in what is called test mode. And so these two modes are usually designed into a chip. And to assert any mode, there will always be some kind of logic levels at some inputs that you apply, and that will determine which mode the chip is in. So often a signal on a dedicated input port will determine if the chip is in functional mode or test mode. So we often sacrifice one input of the chip to serve as the determiner of whether the chip is in functional or test mode. Types of tests. There must be tests for everything on a chip to ensure that there are no defects. So a chip will always have I/O circuits. These are the circuits through which signals enter the chip or depart the chip. And those are special circuits often because of various reasons. One reason is that the core voltage on a chip, the VDD, may be different from the voltage that you use outside the chip. So these I/O circuits will do level conversion from, let's say, 1 volt on the core to 3.3 volts outside. That's an example of a feature in an I/O circuit. And the I/O circuit will have other features also to ensure that chips can interact with the other chips on the board that they are connected to. So I/O circuits are always there, present on a chip. So often clock generation circuits will be on a chip. Example are what are known as phase lock loops. These are circuits that generate the clocks that you use. There will be memories on a chip. There may be analog components, and of course there will be standard cell. There will be standard cells in the standard cell logic. So there can be defects in any of these, and in testing a chip, all these components that are present on the chip will have to be tested, and you have to ensure that there is no defect in anything. What we are going to talk about today is only the testing that we do for the standard cell logic. Okay, so for testing standard cell logic, we use a technique called scan. So again, scan is a technique only for testing the standard cell logic part of a chip. There are other kinds of tests you have to do for I/O circuits, memories, and so on. We are not going to cover that in this class. Those kind of things will be covered in a class on design for testing or DFT. I just want to cover scan because we are focused in this class on how to implement logic circuits involving standard cells, and inevitably any logic circuit, any standard cell based logic circuit will have the scan logic inbuilt in order to enable the testing of that standard cell logic. So it's important to understand scan and how it impacts the design. So let's first look at the challenge of testing logic, basically standard cell logic. So testing standard logic. So if you consider this schematic I've shown here comprising 3 logic gates, each logic gate would be a standard cell. Then it's not, you can think of very easy ways to test this. Suppose your chip had nothing but these 3 gates. If that was your entire chip, then how would you test this chip? Well, it's very simple. You have 4 inputs and you have 1 output. So you can just drive some known logic values on the inputs and check if the output is expected. And if you had only 4 inputs, then you have totally 2 raised to 4 possible combinations of inputs. So that's 16 possible inputs. The 16 possible inputs for a circuit like this. In principle, you could just try every one of those 16 inputs and see if the output is as expected. Okay, and that way you could thoroughly test this circuit. So this is very simple. You see that a couple of points to note here. All the inputs are controllable. So I want to introduce this word controllability. You can see that all inputs are controllable. What do we mean by controllable? It means that whoever is testing this chip is able to put whatever value they want on these inputs. Okay, so the inputs of this combination logic is controllable. You have direct access to the inputs. Then the output is observable. So whatever the output is on the tester, you put a probe at the output and you can see what the output value is. So output of this circuit is observable, inputs are controllable, and controllability and observability is critical in being able to test any circuit. You need to be able to control inputs and observe outputs. So in general, combinational logic can be tested if inputs are controllable and outputs are observable. Okay. If inputs are controllable, you can come up with a set of inputs to test every node in the combinational circuit and determine if it is defective or not. Now let's add some complexity to this combinational circuit. In a typical ASIC, which is sequential and synchronous, the inputs are unlikely to come directly from primary ports. Inputs are likely to come from flip-flops. I've shown a case here where I've taken the same combinational circuit, and instead of the inputs being directly controllable, now the inputs are all connected to flip-flops. And instead of the output being directly observable, the output is connected to a flip-flop. Now, how does this complicate testing of this combinational circuit? Well, it only makes it a little bit more difficult. I simply have to now apply a clock to all the 5 flip-flops. Apply a clock, and then I put the values that I want to drive through the combinational circuit inputs. I put those values as inputs to the flip-flops. Okay, and after the clock edge comes to the flip-flops, those inputs of the flip-flops will go to the outputs of the flip-flops, and then those outputs obviously inputs to the combination logic. So basically, by applying inputs to the flip-flops and supplying clock, I can sort of get pseudo controllability on the inputs of the combination logic. So I can still test this combination logic quite easily. And in fact, I can even test the flip-flops, because if there's any defect in the flip-flop, then any input applied to the flip-flop will not correctly come to the output. So So whatever I'm doing to test the combination logic will also automatically test the flip-flops. So I can do full testing of this, no problem. So if your ASIC only had this circuit, a few combinational gates between some flip-flops, and there's only one logic level, and there's only one sort of the pipeline is only one set of flip-flops at the input and another set of flip-flops at the output, and no other groups of flip-flops, then very easy to test. But now let's keep adding complexity so that we reach the complexity you would see in a typical ASIC. Now here, I've taken that same circuit I showed earlier, combinational logic with 4 flip-flops at inputs and 1 flip-flop at output. But now the inputs of those 4 input flip-flops are not directly controllable. Instead, they come from some other combinational logic, okay? And that combinational logic itself, its inputs come from flip-flops, okay? So this is, now it starts getting difficult to control the inputs of the target combinational logic, okay? And now if I want to send some specific inputs into that combination, into the 3-gate combination logic on the right, then I would have to solve for the combination logic cloud, find out what inputs I should provide to it so that I get the necessary values from its output that I can then send to the 3-gate combination logic. It's very difficult and complicated, okay? And in a typical ASIC, it's even more complicated because, for example, if you have a finite state machine, then the combination, then you can even have like loops, as you can see here. So if you see this here, the combination logic cloud in the middle, some output from that combination logic cloud may actually loop back to the flip-flops that are driving the inputs to that combination logics. That's what I'm trying to show here. So this is a very typical kind of structure of the logic in an ASIC. And it's also important for you to appreciate this, that the structure of the logic in an ASIC, you have registers, or you have groups of flip-flops that are sending data into combination logic, and the outputs of the combination logic is captured by the flip-flops. And then these kind of, and you have multiple such stages in typical sequential ASIC, where flip-flops send data into combination logic. The combination logic's output is captured by the flip-flops, and those flip-flops send data through some additional combination logic, and so on across multiple levels or multiple stages until finally the data arrives at the output. But it's important to know that in this structure, you can even have cases where some combination logic's output cycles back, gets into potentially some other combination logic, and goes into the input flip-flops of that first combination logic. And this structure would always be present if you had, for example, finite state machine logic. So in this kind of a given this typical structure of an ASIC, it's almost impossible for you to be able to control the inputs of this combination logic of these 3 gates that we started with, okay? Even if you do some mathematical solution of all the combination logic stages before you arrive at this target combination logic, even if you're able to solve for that, you would also have a state dependency because of these feedback paths, okay? And so it's essentially, it makes it impossible for you to be able to test if there are any defects in this target combination logic comprising the 3 gates that we started with. Now, the idea is that every node in your ASIC needs to be tested. What do I mean by node? Meaning, let's say if I take this 2-input AND gate, it's driving this XOR gate. So there's a node. We call it a node, the connection between the AND gate and the XOR gate. So we need to find a defect there. The node includes the pins. So every node in this circuit can have a defect, and you need to be able to run tests so that a defect on any node is caught. Okay? And the moment you lose controllability on inputs of combination logic, or you lose controllability to anything, it becomes difficult to test that thing. Similarly, if you lose observability on anything, it becomes difficult to catch a defect. So here, if you look at the output of the XOR gate, it goes to a flip-flop. That flip-flop's output can be an input to some combination logic, and there might be many levels of logic after this, many stages of flop followed by combination logic. So if I want to see what is the output of this XOR gate, it becomes impossible because I have lost observability. Okay, I don't have access to it anymore. It's hidden behind many layers of logic. So bottom line is, inputs of this three, in a situation like this, inputs of any given piece of combination logic are difficult or impossible to control, and outputs are difficult or impossible to observe.